Hello, I'm Tom.
And I'm Mia.
Welcome to the Adaptics podcast. You know, this is our series where we turn these really advanced ideas in artificial intelligence and robotics into, well, simple, clear explanations. I mean, we all know this field moves so fast, and a lot of the time it can feel pretty overwhelming. So our goal is just to create a space where anyone, and we mean anyone, can build their understanding at their own pace. Doesn't matter if you're just getting started or maybe you're exploring the broader world of intelligent systems. Let's dive in.
In this episode, we want to explore how AI systems move from simply generating text to actually reasoning, planning, and acting as autonomous agents, why this shift matters, what enables it, and how it's reshaping the future of intelligent systems.
It's really a fundamental revolution in how we think about what AI can do. For the longest time, large language models, the LLMs, were just phenomenal at one specific thing, prediction.
Right. You give it a sentence starter, and it predicts the most likely next word.
Exactly. The most statistically plausible next word, and then the next, and the next, until you have this incredibly smooth, coherent essay or summary.
And that coherence, it felt like intelligence, but you're hitting on the crucial point. It was an incredibly sophisticated form of pattern matching. They were just passive text generators.
That's the perfect term for it, passive. Because the moment you tried to use them for anything complex in the real world, like booking a multi-stop trip or solving a physics problem,
it would just fall apart.
Absolutely. The initial problem was that lack of reliable multi-step consistency. You need that for any kind of practical goal-directed usefulness.
So you could ask an early LLM to, say, plan out a project.
Yeah, and it would generate a beautiful, confident-sounding plan for the first two steps. But by the third or fourth action, it had often, completely lost sight of the original goal, or the steps it planned were just impossible to actually execute.
So the entire AI community sort of realized that if AI was going to move from being this fancy computational tool to a truly transformative force, an agent, it had to develop a capacity for structured thinking.
It needed to learn how to reason internally before it ever produced that final output.
And that's really the dawn of simulating thought.
It is, because when these LLMs faced complex, multi-layered tasks, their outputs were just erratic. They didn't have a robust internal way of tracking progress or applying logic. Think about it like trying to calculate your taxes entirely in your head versus writing every single step down on paper.
Writing it down forces you to be accountable. It gives you structure.
That's it. And that structured approach in the AI world is what we started calling chain of thought, or COT. It was a foundational shift.
A huge breakthrough, wasn't it?
A massive one. COT basically involves the model generating a series of intermediate natural language steps. An explicit rationale, you could say. It does this between the initial prompt and the final answer.
So it's essentially forcing the model to talk itself through the problem.
Yes, to simulate structured, deliberate reasoning. It verbalizes its internal steps, which makes the whole process more traceable, and critically, it drastically improved accuracy on complex reasoning tasks, especially things like mathematical word problems.
It's like we're requiring the AI to show its work on a test. We can actually see the entire path it took, which is great for understanding why it got an answer.
Exactly. It boosted performance on benchmarks like GSM-8K dramatically, but there was a significant limitation with that initial version of chain of thought.
It was still all happening inside the model's head, right? Confined to its internal static knowledge.
That's the sticking point. That's the wall they hit. ET makes the AI a better internal logician, for sure. But what if the task required interacting with the real world, like needing to know the real-time weather in London or searching a private database?
The model couldn't reach outside its own brain. It couldn't act.
It couldn't act, and it couldn't update its knowledge based on any kind of external feedback. It was a closed loop.
But wait, if the AI is so good at reasoning with chain of thought, why couldn't it just, simulate the external world internally? Why did it need a separate tool for something as simple as a Stark price?
Because internal simulation, no matter how powerful, is limited by the model's training date. And more importantly, by the sheer unpredictability of the real world. You can't simulate a live, constantly updating data feed.
You have to actually check it.
You have to check it. And this gap, the need to both reason and act, is what led directly to frameworks like React.
React, reasoning and acting.
That's it. And this was the first major step toward what we now think of as autonomy.
So how did React bridge that gap? What did it do differently?
React was revolutionary because it let the LLM adapt its reasoning dynamically. It could now act on the environment and then receive real-time feedback. The whole workflow changes.
It's not just thinking anymore.
Right. The AI generates a thought, that's its internal reasoning. Then it generates an action, like calling a search tool, and then gets an observation back from the environment, like the search results.
And that observation then feeds into the next thought.
Precisely. It informs the next thought and the next action. It becomes a cycle.
So the AI is much more grounded in reality now. It's not just guessing the next word. It's like it's running the scientific method. Hypothesize with a thought, test it with an action, and then observe the feedback.
That's a perfect way to put it. There's a fantastic complex environment they use to test this called ALF world.
Right.
In ALF world, the agent gets a task, like cool some pan and put it in the countertop. To do this, it has to perform a whole sequence of actions using these simple text commands, like go to receptacle or open object.
So can you walk us through what that would look like with React? Say, for that task, put a cold pan on the countertop.
Sure. So it starts. Step 1, a thought. Okay, I need a pan and I need to cool it. I should probably start by searching for a pan in the cabinet.
Logical first step.
Then comes the action. It outputs the command search, cabinet 1. Then it gets an observation back from the environment. The pan is not in cabinet 1.
Okay, so its first attempt failed. What now?
Now it adapts. It generates a new thought. My initial hypothesis was wrong. I need to expand my search. I'll try cabinet 2. So its next action is go to receptacle cabinet 2 and then open object cabinet 2.
And hopefully this time.
This time the observation is found a pan. So its next thought is, great, I have the pan. Now I need to cool it. I should probably use the fridge. And the cycle continues.
That iterative loop is what proves it can handle these long sequential tasks. It can adapt based on failure or partial success.
Exactly. But there was still a problem. Even with React, if a really long sequence of actions fails completely, the agent still has to start over from scratch. And it might make the same strategic mistake again.
How do you solve for that kind of persistent failure?
That led to the next step, to systems like reflection. The idea here is if the agent's entire plan fails, it gets, an explicit status. Fail signal after 20 steps. It needs a way to learn from that failure without needing to be completely retrained.
So reflection sounds like the AI is taking a moment after a failure to almost journal about what went wrong, to identify the point of error.
That is a perfect way to put it. Reflection adds this crucial verbal reinforcement step. If the agent fails, it generates what's called an adaptation text or a reflection.
And this reflection synthesizes the error.
Yes, and it modifies its internal reasoning for all future attempts at that same task, or even similar tasks.
So the key insight here isn't just fixing the error in that one moment. It's about permanently updating its internal strategy based on a single failure. That's a level of persistent learning that previous models just couldn't do.
Exactly right. We've seen examples where an agent failed a task because it only found one of 2 required ingredients and then just stopped, prematurely thinking the task was complete.
And the reflection would help it realize that.
Yeah. The reflection text it generated after the failure explicitly said something like, my goal requires 2 items, not 1. I must check the counter again for the second item.
So in the next trial, it automatically incorporates that higher level strategy.
It does. It builds that realization into its new action sequence from the start, and that leads to success.
So the trajectory here is just crystal clear. You go from simple internal thinking with Coty to thinking and doing with React, and then finally to thinking, doing, and actively learning from your mistakes with reflection.
And that progression is the foundation. It's what transforms an LLM from a simple generator into a strategic adaptive agent.
Okay, now that we understand how these models can simulate thought and action, let's talk about the next critical piece for autonomy: planning. A lot of people seem to mix up planning with prediction. How are they fundamentally different in an AI context?
This is such a crucial distinction. It's really what separates a simple chatbot from a truly autonomous system.
Yeah.
Simple prediction, which is the foundation of traditional LLMs, is very localized. It's short-sighted.
It's all about generating the next likely word, the next token.
Yes, just to maintain that statistical coherence. True planning, on the other hand, is all about the long term.
Meaning what exactly?
Planning is about maximizing a long-term reward or reaching a complex goal by simulating the entire sequence of consequences before you even take the first step.
So it requires foresight and risk assessment and really understanding how the environment works.
Absolutely. A predictive model says, if I start this sentence, the next word is probably apple. A planning model says, if I take this action now, I can predict that in 3 steps I will reach the goal, avoid these obstacles, and my overall long-term reward will be high.
And that's where even early planning LLMs, even with chain of thought, often struggled. On those long horizon problems, they'd get distracted or stuck in what's called a local optimum.
Precisely. They achieve a small, immediate win, but completely miss the bigger ultimate goal. They just lack a complete conceptual framework for understanding the world, kind of like how a person understands basic physics.
Which brings us to the need for more structured architectures, like the law framework.
The law framework language, agent, world. It's a really comprehensive system. The idea is that robust, versatile reasoning needs more than just the language model by itself.
It needs these three interconnected pieces.
Right. And all of them use the language model as their computational backbone. You need a way to model the world, a way to model the decision maker, and then the LLM provides the underlying power.
Let's break those down. First, the environment simulation, the world models.
The world model is basically the agent's internal simulation engine. It lets the agent predict future states that will result from different actions. It's essential for anticipating consequences.
So if an agent is trying to move a package across a warehouse,
The world model predicts what happens if it hits a wet patch, or if a door is unexpectedly closed, or if another robot moves into its path. It's this internal simulation that it uses for strategic, forward-thinking problem solving.
it's building a little mental map of reality, and the agent model then is the one using that map to direct the operation.
Correct. The agent model has all the crucial elements for human-like reasoning. This includes the agent's core beliefs about the current state. Where are the obstacles, its goals and rewards, the function it's trying to optimize, like deliver this package as fast and as safely as possible, and of course, the actual strategic planning process itself.
So in this framework, the language model isn't doing the reasoning directly in a vacuum. It's serving as the versatile backend that actually implements these more sophisticated agent and world model components.
That's the critical innovation. See, previously, if you wanted a system for planning, you might use a classical symbolic planning language, something like PDDL.
Planning domain definition language.
Right. And PDDL is great for stable, simple environments because it's all based on predefined rules and verified logic. But it's totally rigid. It cannot adapt to complexity.
And the LLM, by acting as the computational backend, provides that adaptability that a PDDL system just doesn't have.
Exactly. And that adaptability becomes so crucial in dynamic, real-time situations. Think about a complex simulation, like the land war game simulation, where agents have to operate under real-time battle conditions with the fog of war.
So the environment is constantly changing, information is incomplete.
And the rules can shift on the fly. A PDDL-based system would just freeze up because its fixed rules are suddenly violated. But an LLM, acting as the agent model, can use its vast contextual understanding to synthesize that partial observation from the world model and generate an adaptive plan that maximizes its expected reward.
Even if that means something like prioritizing survival over the immediate objective.
That's a perfect example.
Let's simplify that agent model in action. If we go back to the example of a robot getting the command, "Give me a cup."
Okay, so that command kicks off a strategic plan. First, the agent uses its belief system to figure out where a cup is likely to be. It knows cups are usually in kitchens or dining rooms, not bathrooms.
Right.
Then it combines this with its world model, simulating different paths, estimating the travel time, avoiding obstacles. And all the while, its goal-reward system is active, optimizing for the path that finds the cup quickly while using the least amount of energy.
So the combination of those three things generates the optimal sequence of actions.
Yes, and it overcomes the biggest limitation of earlier models. They just lack that internal model of goal-directed consequence. This architecture ensures the AI doesn't just generate a plan that sounds plausible, but one that is strategically optimal, grounded in a continuously updated, simulated reality.
We've established the foundation, structured reasoning like React and strategic planning with the law framework. That leads us to the final form, agentic AI. For our listeners, what's the clear definition that makes a system truly agentic instead of just a really smart chatbot?
Agentic AI really refers to systems that exhibit autonomous decision-making, continuous learning, and goal-oriented behavior. The key is that they can adapt based on real-time data and evolving objectives without constant human supervision.
They're proactive, not reactive.
Fundamentally proactive. They are capable of continuous operation toward a complex goal. They don't just take one instruction and spit out one static answer.
Instead, they're entering this continuous iterative cycle that really defines their whole existence. Can you walk us through that core loop?
The core loop of agent behavior is this iterative cycle: act, reason, plan, and adapt. It all starts with strategy development. The agent gets a high-level goal and has to break it down into a sequence of actionable, concrete steps.
Then comes the execution.
And then execution, yeah. Carrying out those tasks, using whatever tools it has available. And after that, it performs a rigorous outcome evaluation. Was the goal achieved? Did my action produce the result I expected?
And if the answer is no, which it often will be, then the agent has to adapt. That's the iterative refinement step.
Exactly. If the outcome is unsatisfactory, the agent refines its strategy, adjusting its internal beliefs or its future actions based on that failure. This loop is continuous. A standard LLM stops after its first output, and agent restarts the loop based on the external feedback it got from that output.
That evaluation and refinement part seems to rely heavily on memory. I mean, for humans, we get better by reflecting on our past experiences and failures. How do agents emulate that?
That's the critical function of what's called memory reflection. And it's not just about saving a transcript of a conversation. Agents have to engage in a process that emulates human summarization and long-term refinement.
So they synthesize historical interactions.
Yes, and they store those key insights in their memory systems. This allows the agent to generalize successful strategies and avoid past mistakes, which massively enhances its adaptability when faces a new environment or a slightly different task.
So, if an agent fails a complex coding task 3 times in a row, the reflection step would summarize the common point of failure like, I keep misinterpreting the API documentation on authentication, and that new insight guides the next attempt.
Precisely. It's persistent learning, applied efficiently. And crucially, they can achieve this behavioral improvement without the massive computational cost of retraining the entire underlying model every single time they learn something new.
How is that possible? How can the behavior change without altering the core model weights?
That's where feedback learning comes in. Agents can reinforce their policy generation using feedback, often just as context, rather than needing a full, expensive model weight update.
And that feedback can come in different forms.
Very versatile. We've already talked about verbal feedback, like the reflection text and reflection, but a major advancement came from integrating human-in-the-loop training.
You're talking about frameworks like RLHF and DPO, which involve human preference rankings?
Exactly. RLHF, or Reinforcement Learning from Human Feedback, and its successor, DPO, Direct Preference Optimization. These are methods where the agent generates several possible actions or outputs.
And then a human comes in and ranks them?
Yes, human annotators rank those outputs on criteria like which one was safer, more helpful, or more aligned with what the user actually wanted.
So instead of trying to optimize for some complex, abstract metric, the agent is just optimizing for what humans prefer.
That's it. This preference ranking serves as a direct feedback signal to adjust the agent's behavior. The agent learns that if it chooses action A, it gets a higher human preference score than action B, so it reinforces action A in the future.
Which is computationally efficient.
Very. And it's incredibly effective in complex applications, like making sure a healthcare agent generates treatment suggestions that are not only technically correct, but also communicated in a clear and empathetic way.
So the agent is constantly calibrating its internal policy, whether that's based on environmental rewards, human preference, or task completion. This continuous calibration is what allows it to be truly autonomous.
It is the continuous learning loop. Even in highly complex environments like that land war tactical AI system, the agent is constantly updating its planning strategies based on the expected value of its decisions, using that feedback to ensure it maximizes its long-term strategic gain.
Okay, so once an AI has this sophisticated internal loop for reasoning, planning, and self-correction, the next logical step is to break out of the prison of its static training data. How do tools and external data sources completely transform an agent's capabilities?
Tools are the equivalent of giving an isolated genius a telephone, a laptop, and a library card. By its very nature, an LLM's training data is static. It stops knowing things after its last update. Tools they shatter that internal knowledge barrier.
They transform the LLM from a self-contained brain into a coordinator.
A coordinator that can use the entire digital ecosystem in real time. This is all achieved through tool use and function composition. Modern AI systems can integrate external APIs, search engines, databases, calculators, anything really directly into their reasoning workflow.
And frameworks like LangChain or Crew AI are kind of the operating systems that manage all of this.
They are. They let the agent analyze a prompt, define a goal, and then strategically pick the right tool or sequence of tools for each subtask.
And this dramatically increases accuracy because the agent isn't guessing anymore. It's pulling verified real-time information. The core technique that enables this is retrieval augmented generation, or AG.
RAG is an incredibly important method. It means the LLM, before it answers, first uses a retrieval mechanism to go and access an external knowledge base. This isn't just the whole web. It's often a specific, verified set of documents, knowledge graphs, or company data.
Can you give us a quick example of that?
Sure. Imagine you work for a large company, and you ask an agent about the new remote work stipend policy. The LLM itself knows about general remote work trends, but it doesn't know your company's specific new policy.
Right.
So RAG ensures the agent first retrieves that relevant internal policy document, and then the LLM generates an answer based strictly on that retrieved, verifiable context.
Which means the response is grounded, in fact. It avoids hallucination and ensures it's actually relevant.
Yes. And as agentic AI evolves, we're seeing these advanced workflows that use multiple specialized agents for different tool-using roles. We call it agentic reasoning. This is where you see a true division of labor.
What's an example of that kind of specialized team at work on a really hard problem?
Let's say you're trying to design a new alloy. You might have 3 distinct agents collaborating. First, you'd have a dedicated web search agent for sourcing scientific literature. Second, a coding agent for running simulations and physics models.
And the third?
And third, maybe a mind map agent, designed specifically to build a structured knowledge graph to organize all the logical relationships and dependencies they discover. This coordinated workflow can tackle problems far beyond what a single LLM could manage.
That division of labor is incredibly powerful. And the absolute cutting edge of tool use seems to be interacting with the computer interface itself. So the agent can use a spreadsheet, a browser, any application we can. These are the GUI agents.
That is a colossal step toward practical full autonomy. GUI agents are designed to interpret the graphical user interface. They can analyze a screenshot of a desktop and translate a natural language instruction like go to settings and change the font size into precise desktop actions.
You mean literal cursor movements, clicks, and keystrokes?
Exactly that. We saw the Claude 3.5 computer use model demonstrate this. It achieved successful task completion in 16 out of 20 test cases on a benchmark that simulates everyday computer tasks. That level of digital dexterity means the agent can essentially use any application a human can, which opens the door to automating incredibly complex software workflows.
That closes the digital loop. But what about the physical world? An agent needs to interpret visual data to know where that cup is.
That takes us directly to multimodal migration. For embodied agents, robots, industrial systems, to really perceive their environment, you need feature fusion. You have to integrate non-text data like visual input and audio.
This requires systems like visual language models or VLMs.
Exactly. Models like Mini-GPT-4, which can process an image and connect what it sees to its language capabilities. So the agent gets a command, it processes the visual input to locate objects in 3D space, and then it combines that perception with its text-based planning rules to generate a sequence of physical movements.
It closes the loop between the strategic plan and the observable physical environment.
That's the goal.
So we've established that a single advanced agent can reason, self-correct, and use tools. But if one human can't build a whole piece of software or run a massive factory alone, we shouldn't expect one AI to either. This seems to point directly to multi-agent systems.
Collaboration becomes absolutely essential. Many complex tasks, from large-scale software engineering to industrial simulation, are just too extensive or too specialized for one single monolithic agent. Distributed reasoning lets us leverage complementary strengths.
How does that collaboration actually work? Is it just a messy group chat, or is it highly structured?
Oh, it's highly structured. Usually it's built around role specialization. Frameworks can assign specific, often human-like roles to different agents. A great example is the Meta-GPT pipeline for software development.
Okay.
Your distinct agents acting as the product manager, the chief architect, the coder, and the tester. And each one follows standardized operating procedures specific to their role.
It's an instant project team. It can handle a scope that would just overwhelm a single agent. We're also seeing systems designed purely for enhanced reasoning, like the CoPlanner framework. How is responsibility divided there?
CoPlanner is fascinating because its structure is designed to leverage the specific weaknesses and strengths of LLMs. It uses 2 distinct agents, a planning agent and a reasoning agent.
Okay, so a strategist and an executor.
That's a perfect way to put it. The planning agent focuses on the high-level strategy. It selects the meta-strategies and generates concrete hints to guide the process. The reasoning agent, on the other hand, just focuses on the step-by-step execution, strictly following the hint provided by the planner.
And the insight there is that LLMs are really good at following concrete instructions, but they can struggle with that high level of strategic planning on their own.
That seems to be the key finding. By separating these duties, they cooperate much more effectively. You have the strategist overseeing the meticulous executor.
But does just adding more agents or more interaction always lead to better performance?
Interestingly, the research suggests no. Multi-agent reasoning does not always guarantee a better result, especially if the underlying model is already very powerful. A key finding is that low-quality feedback or just redundant chatter can actually confuse the reasoning agent.
It can cause it to reverse a correct answer.
Exactly, which underscores the importance of high-quality communication and clear protocols. It's not about more interaction, it's about better interaction.
And beyond cooperation, agents can also use adversarial interaction to get better outcomes, right? Like simulating a debate.
That's the competitive approach. With systems like Chat-Eval or MAD, the goal here is to foster divergent thinking. By having multiple agents take opposing viewpoints or critique each other's solutions, they can overcome issues like thought decay.
Which is when a single agent just gets stuck on a failing strategy and can't break out of the loop.
Right. A debate forces scrutiny and adjustment. It simulates that collective wisdom of human evaluators.
And as all these agents from different companies and different systems start trying to collaborate, they're going to need a standard way to talk to each other.
Absolutely. This requires dedicated communication frameworks for interoperability, like the agent-to-agent or A2A protocol. This is essentially creating a common language, using standards like HTTP so that autonomous agents can collaborate seamlessly, regardless of who built them. It's the backbone for this whole ecosystem to function at scale.
This entire movement from passive text generation to active collaborative agents represents a fundamental strategic shift. We're moving from what's called the co-pilot model to the autopilot model. How do you define that evolution?
The co-pilot model views AI as an assistant. It operates in a human-in-the-loop framework. The AI supports and enhances human work, it increases productivity and reduces errors, but it still requires human supervision and validation.
It's an efficiency multiplier for the worker, but the human is still the safety net.
Precisely. The autopilot model is the next strategic goal, AI operating autonomously. This focuses on continuous learning, which dramatically reduces the need for human supervision and therefore lowers operational costs. The efficiency gains are massive, but the need for robust safety guardrails becomes non-negotiable.
And we're already seeing this transition produce really concrete, measurable results across major industries. Let's start with a high-stakes field like healthcare.
In healthcare, the impact of multi-agent systems is genuinely transformative. Take a diagnostic system like Zodiac. It uses a multi-agent architecture to process all sorts of patient data images, lab reports, doctor's notes, aiming for what they call cardiologist-level diagnostic support.
And the result?
By integrating all this data and vast medical knowledge bases, these systems have been shown to reduce diagnostic errors by up to 30%. That's a huge number.
A 30% reduction in diagnostic errors is a staggering statistic. What about in industrial manufacturing, which is all about sensor data and complex continuous decisions?
In manufacturing, agentic systems are handling those continuous planning tasks in dynamic environments, exactly where the old symbolic systems used to fail. They use their perception layer to get real-time sensor data equipment status, temperature, production line info, and they learn the optimal strategies for dealing with complex rules and unexpected events.
Like a sudden equipment failure.
Exactly, which results in huge efficiency and quality improvements without a human engineer needing to constantly supervise.
And in finance, where speed and consistency are everything.
In finance, we see a dual impact. First, efficiency. AI-driven fraud detection systems have cut fraudulent transactions by as much as 40% for early adopters. They can spot complex patterns in real time that humans would miss.
And the second impact?
Second, multi-agent reflection frameworks are enhancing financial Q&A that involves complex numerical reasoning. They often have a dedicated critic agent whose only job is to rigorously evaluate the intermediate reasoning steps and the final numbers, ensuring reliability of those high-stakes calculations.
It seems agentic AI is also starting to accelerate the pace of scientific discovery itself, becoming a collaborator in research.
This might be the most exciting application of all. Researchers have set up collaborative LLM agent laboratories in simulated environments like Agent Drogfa, where agents share research reports on a simulated preprint server. They build on each other's work.
And this collaboration makes them better.
Significantly better. Studies show that when multiple agent labs share and collaborate, the overall accuracy of the group increases by about 13.7% compared to agents working in total isolation. It demonstrates a future where AI is actively generating, testing, and refining hypotheses right alongside human researchers.
It's clear this shift to autonomy delivers massive gains. But as that power and autonomy increase, so does the risk. We have to talk about the necessary governance and the guardrails.
When you grant an AI system the ability to act and plan without constant human checks, you introduce new layers of security and ethical challenges that are far more serious than what we faced before.
Let's start with the most fundamental concern: data and privacy.
Data vulnerability is paramount. These agentic systems have to process vast amounts of sensitive data, whether it's patient data in a hospital or proprietary manufacturing rules. This massive decentralized data volume makes them highly vulnerable to breaches. Strong security, strong encryption. These are non-negotiable foundations.
And since these agents are making complex, sequential decisions, they're also facing sophisticated attacks that target the planning mechanism itself, trying to trick them into making a bad decision.
Exactly. Attackers can disrupt the decision-making process in a few ways. One is through adversarial example attacks, adding these subtle, imperceptible changes to the data input. To a human, it looks completely normal, but to the agent, that tiny perturbation causes it to make an entirely wrong decision.
So the agent sees the data differently than we do and gets tricked into choosing the wrong path or generating a harmful response.
Precisely. Another threat is even more direct, corrupting the learning process itself by injecting malicious samples into the training data, or even more dangerously, tampering with the reward signals.
If you corrupt the reward signals,
You can induce the model to learn entirely wrong, harmful strategies.
it's like teaching the agent that jumping off a cliff gives it a high score. It learns the wrong definition of success.
That's a great analogy for what's sometimes called harmfulness planning. The agent's critic model, the part that scores the goodness of an action, can be taught to give high scores to decisions that have no positive gain but just conform to the attacker's malicious preferences. The agent is trying to maximize its score, but the goal it's maximizing is corrupted.
So how do we mitigate these profound risks when the planning mechanism itself can be targeted?
We need multi-layered mitigation strategies. It starts with stringent verification and cleaning of all training data. Then, during the decision-making process, you need continuous monitoring of the core components, the actor model that takes the action and the critic model that evaluates it.
And securing those feedback signals has to be just as important.
Reward signal verification is critical. You have to encrypt the transmission of those signals and continuously compare them with actual environmental rewards to ensure the integrity of the feedback loop. And we're also using advanced techniques like adversarial training, which is where you intentionally expose the AI to these attacks during training to help it learn to identify and resist them.
There's also the challenge of stability that isn't malicious, but just suboptimal. The problem of generative content being inert.
Right, inertness planning.
Yeah.
This is an internal issue where the agent ignores a sequence of actions that could achieve a positive gain simply because the critic model doesn't recognize it. It doesn't conform to its conventional learned preferences.
So the agent fails to do something beneficial because it's not the path it was trained to expect a high score on.
Exactly. Eliminating these inert or harmful generative behaviors is a huge area of ongoing research, and it's essential for making these systems truly reliable in the real world.
Which highlights that even when the agent is trying to succeed, its own internal reward structure can sometimes get in the way.
That's right.
We've covered the limitations and the necessary guardrails, which brings us to the final and maybe most promising strategic direction: the move toward hybrid intelligence. What does that mean for system architecture?
Hybrid intelligence is all about integrating the complementary strengths of two core paradigms, the symbolic and the neural. The symbolic paradigm is classical, rule-based AI. It gives you verifiability, logical soundness, plan optimality. It makes systems auditable and trustworthy.
And the neural paradigm, driven by LLMs, provides the adaptability and raw power to handle messy, unpredictable, real-world scenarios.
Exactly. The most viable path forward is combining them. We need the neural adaptability of LLMs to handle complex data, but we need the symbolic rigor to formally verify critical goals and safety constraints. It allows us to build agents that are both highly adaptable and inherently trustworthy.
Beyond the architecture, the deployment landscape is also changing, especially when you're dealing with sensitive data like in healthcare or finance.
That's why we're seeing the rise of federated agentic AI. These are systems that let intelligent agents learn from decentralized data spread across multiple locations, without exchanging the raw sensitive data itself.
Which is vital for privacy.
Absolutely. It lets agents collaborate and learn collectively while preserving user privacy and organizational security.
And for businesses that want to adopt these tools without building huge AI teams, we're seeing the rise of AI as a service, or AAs.
AAs is the commercial model, where these complex multi-agent systems are offered via cloud platforms. It lowers the technical barrier to entry for a lot of organizations, but does raise new challenges around transparency, since the model is a black box, and ensuring stability when thousands of agents are running at once.
There's also a big distinction emerging in the tools used to build these agents between the open source community and commercial platforms.
For sure. On the enterprise side, you have platforms like Crew AI, designed for managing complex multi-agent setups. LangGraph is another powerful one, focused on customization and reliability for intricate workflows.
And on the open source side, which is more about transparency and flexibility.
There you see tools like AutoGen, which is really tailored for developers and collaboration between agents, and AutoGPT, which is aimed more at enthusiasts and lets an agent autonomously break down big goals into subtasks. Having both these ecosystems means innovation is just happening at a breakneck speed.
And as this field matures, the way we evaluate these systems has to evolve too. We can't just test if they can retrieve a single fact anymore.
The evaluation paradigm is shifting profoundly. We're moving toward benchmarks that measure an AI's robustness in everyday human-level reasoning tasks. The GAI benchmark is a perfect example. It has questions that are conceptually simple for humans. We solve them with 92% accuracy.
And the best AI models.
Current state-of-the-art models, even with all the sophisticated tools we've discussed, only achieve around 15% accuracy on it.
Wow, 92% for humans versus 15% for advanced AI. That gap is stunning. It really emphasizes that we're now demanding agents that can mimic the resilient, general-purpose reasoning of an average person.
It's a huge indicator that we've successfully transitioned AI from a passive generator into an active strategic planner. The focus now is on making that planning process as reliable and versatile as human cognition is in all sorts of messy practical scenarios.
So, to synthesize this entire transformation, AI systems are no longer just conversational partners that rely on prediction. They are increasingly autonomous collaborators that can reason through multi-step logic, strategically plan using internal world models, adapt based on real-time feedback, utilize external tools, and operate across complex, real-world workflows like diagnostic support and software development.
The shift is fundamental. We're moving from AI assisting in execution to AI dictating and managing the strategy.
This leaves us with a final provocative thought. If AI systems are increasingly adept at generating high-quality research reports, analyzing complex data sets, and formulating innovative research hypotheses, as demonstrated by those collaborative agent systems, what becomes the long-term role of the human scientist or the human executive? We are shifting the human role from executor and hypothesis generator to high-level director, focusing our unique creative input at the very beginning when defining the grand strategy and at the end when interpreting the results.
That evolution of the human-AI partnership is certainly something worth thinking about as these autonomous systems mature.
Thanks for listening to the Adaptix podcast. If you have any questions, feel free to reach out to us.